kids, we're going to do two things today, neither which is going to teach you new math. It's all based on math that you've already done. I'm just going to teach you some new vocabulary, really. So you know the idea of convergence being an infinite sum, right? We're talking about having an infinite sum, and whether that sum you're adding smaller and smaller numbers such that you reach an upper bound, right? Where no matter how many terms you keep adding, the numbers are so infinitesimally small that you never go above a certain sum. And however, if you diverge, you're going to grow, the sum is going to grow without bound. So absolute convergence does have to do with absolute value. Absolute convergence means the series will converge regardless of the signs of the terms. Signs are all positive, signs alternate. Doesn't matter, you're going to converge either way. So for example, here is an alternating numeric series. Does this series converge absolutely or conditionally? That's the question. Absolute or conditional convergence. So the first thing we do is just look at this numeric series and see if it converges. It's got a sign alternator, so I'm going to run the alternating series test on it. Alternates, terms get smaller and smaller with the 2n plus 3 factorial in the denominator. Therefore, this series converges with the alternating series test. But does it converge absolutely or only conditionally? To answer that question, you have to go one more step and say, these terms that I had, right? N is equal to 1. So if I expand these terms, I get negative 1 over 5 factorial plus negative 1 squared over 4 plus 3 factorial minus so that sum converges by the alternating series test, right? You're going to have negative, positive, negative, positive. So every other term, you're adding something negative, which means you're pulling your sum back down from the roof of the house. So was the only reason this series converged, though, my negatives? That's the question. The fact that every other term was negated, was subtracting. How I answer that question is taking the absolute value of the terms and saying, do I still have a convergence series? I have to do the ratio test on this. And if I do the ratio test, right, the ratio test on this would be the limit as n goes to infinity of 1 over, replace the n with n plus 1. That would be 2n plus 2 plus 3. So that would be 2n plus 5 factorial. Reciprocate, right? Then you're going to divide by the original, which means 2n plus 3 factorial is going to go on top here. Expanding 2x plus 5 factorial, I'm going to be able to cancel 2n plus 3 factorial and be left with 2n plus 5 times 2n plus 4 in the denominator. That limit is 0. 0 is less than 1. Therefore, this series that I took the absolute value of, which means I turned all my terms positive, still converged by the ratio test. Still converged. Therefore, my original series doesn't just converge, it converges even if the sign alternator isn't there. It converges absolutely. So that was an example of an absolute convergence. What if it's not absolute convergence? It's conditional. What is the condition? That the signs alternate. So here's a pretty famous, right? The alternating harmonic series. It converges by the alternating series test. The signs alternate. Without the alternator, they're all positive and they go to 0. Therefore, converge by the alternating series test. So if I write out some terms, I get -1 plus 1/2 minus 1/3 plus 1/4. Every other term is negative. Therefore, as I'm summing positive, I sum a positive with a negative, then a smaller positive with a smaller negative, then a smaller positive. That sum converges. If I want to know what kind of convergence, I want to know, will this series still converge if the signs are all positive? I take the absolute value of my series, and this time I got the regular harmonic series, which when I put in 1, I get +1, +2, 1/2, +1/3, +1/4, yada, yada, yada. This series diverges because it is a p series with p is equal to 1, so no. When you take the absolute value, you don't get a convergent, which means my original series only converged because I had alternating signs. I have to have alternating signs or this series will not converge. So we say this series converges conditionally. And again, the condition is that your signs alternate. The previous one, it didn't matter whether my signs alternated or not. I had a convergent series regardless. That's converging absolutely. So this was absolute and conditional convergence for a numeric series. Let's do a power series. This is what I was talking about, no new math, right? You have done this. Find the interval of convergence of a power series. Means you do the ratio test where you suck out the x and then you find the radius of convergence. I'm not going to do that work. I'm going to tell you that we did the radius of convergence and we got 2, but the ratio test uses absolute value. It already tests for absolute convergence, right? Because the ratio test is the limit as n goes to infinity of absolute value, and you put your terms in here. So when you put this whole series in absolute value bars, the sign alternator is ignored. The radius of convergence is 2 with a center of 0. That means the power series converges absolutely on the open interval -2 to 2. We just didn't use the word absolutely before. We just said the radius of convergence is 2. But now I'm going to turn that into an interval and say the power series converges absolutely, -2 to 2. You want to find the interval of convergence, so you need to check the endpoints. First, put the left endpoint in, shake it all about. You have a sign alternator. When you simplify this, you end up with a p series where p is equal to 1, and therefore you diverge. So the left endpoint is not included in the interval of convergence, but when you put the right endpoint in, and again, you still have the sign alternator, the right endpoint creates a series that converges by the alternating series test. So you would write the interval of convergence is open interval on -2, closed at 2. But the new vocabulary that I want you to add, this series converges conditionally at that right endpoint. What was the condition for the right endpoint? That you had the sign alternator. Right? So again, go back up to here. The power series converged absolutely. You pick any number in between -2 and 2. You use the ratio test on those numbers, which made it absolute, which means when the signs were all positive, you got convergence. Therefore, if you add a sign alternator, it's just going to make the sum smaller, so it's obviously going to converge as well. The left endpoint is just out of discussion because it created a divergent series. The right endpoint did converge, but the convergence depended on the sign alternator. So you say the series converges conditionally at that right endpoint. All right, we'll do another example of that in our next live session, but now we're going to move on to the second objective. And the second objective is just to give you another test a convergence, why can't I say that? Test for numeric series. The ones that you have already are the geotest for convergence, p-series test, you have comparison test, you have the alternating series test, and you have the ratio test. I'm going to add one more called the integral test. And the integral test goes all the way back to the beginning of this unit when you learned how to do improper integrals. So here's the formal definition, but I'll tell you what the important pieces here are. You do have to have no alternating. All your terms have to be positive. As long as you can take your series and rewrite it as an improper integral, and then evaluate the improper integral. And if you find out the improper integral converges, then the series based on that you base the improper integral will converge as well. Or if the improper integral diverges, then the series that you base the improper integral on will diverge as well. Pretty cool. You just have to be very careful that just because the improper integral converges to a number, that means you'd be able to get to a number. The series doesn't necessarily converge to that same number. Okay, the series does not. Because remember, when you're doing an improper integral, you're really summing areas of rectangles. Right? When a series, you're just summing terms. So that's why when they converge, if the improper integral that you wrote based on this series converges, it doesn't guarantee that this series converges to the same number. So you do have to have a continuous, positive, but decreasing function for some n, right? It doesn't have to be the beginning. It doesn't have to be this n. It just has to be somewhere close. So let's do one. So does this integral converge? Now pretend you don't know that's actually a p-series, right? That's n to the first. That's really n to the first and n to the 1/2 times n to the 1/2. That's really n to the 3/2, right? Pretend you don't know that yet. I'm going to ask you to do the integral test on it. And look what I did. I took this numeric series and turned it into a function, which is continuous, positive, and decreasing after 1, or from 1 on. If the improper integral converges or diverges, then the series I base that integral on will do the same, just not necessarily to the same number. So here's what I did. Here's my improper integral. I remember my improper integral work, where I put a limit out front. I replace the improperness with a, and then say the limit as a goes to infinity, and then I ignore all the limit stuff. And I integrate. X to the negative 3/2 is something I can integrate. It's x to the negative 1/2 divided by negative 1/2. That's where this negative 2 comes in. I'm going to evaluate that at a and 1. X to the a to the negative 1/2 is really a to the 1/2 square root of a in a denominator. And then remember, it's minus the negative 2, which is why I have a plus 2. I'm going off to infinity. So what does the square root of infinity go to? Infinity. And what is negative 2 over really, really, really big numbers? 0. So the improper integral equals 2. Therefore, by the integral test, the series that I built the integrand from converges. I just can't say it converges to 2. Okay? That's how you use the integral test. The integral test is really improper integral work. The integral test is where the p-series comes from. Isn't that kind of cool? Right? I can integrate 1 over n to the p in the abstract, just keeping p right in there. Don't put a number in for p, and I can prove that that improper integral will diverge if p is 1 or smaller than 1, but converge as long as p is greater than 1. That's where the p-series test comes from, which is why I wouldn't really use the integral test on this. I would use the p-series test. All right, so we'll do an example in our live session, one that is not a p-series, and your homework will have some of these. So you will have some homework that is both on absolute and conditional convergence, as well as doing the integral test on a numeric series. Remember, don't use the integral test if you recognize a p-series. That's no integration. All right, I will see you in our next live session.